So I was looking at, or somebody mentioned JASP to me, and I was looking at this, and one thing that I do like is if I zoom in, control and zoom in, there we go. So what is this thing anyway that I'm looking at? JASP, right? It says a fresh way to do statistics. So someone mentioned this to me, and there's someone that doesn't code, so they kind of like get the statistics out of these models, and even Excel might be a bit too much for them because they have to kind of like know these statistics, or at least how to build some of the statistics, even as simple as Excel makes it. And the same thing for like Google Sheets and other software like that. So they kind of like mentioned JASP, and it's this fresh way to do statistics, and you can download JASP. But the one nice thing that I like about this is straight away I see that JASP is an open source project supported by the University of Amsterdam, and there are some pretty smart people there. So not only is it open source, but it's supported by what appears to be possibly a good community, but I don't know how big it is. It's an intuitive, friendly interface that was designed with the user in mind. And I went along and watched one 4 or 5 minute video and then another 10-minute video. I haven't even done the download. I probably won't even do the download at this point in time, but I'll just go through a couple of the features with it. JASP offers a standard analysis of procedures in both their classical and Bayesian form. And the reason why I'm not going to do any or like download it and new stuff is I obviously for all of the stuff that I do, I tend to use Python quite a bit, and it appears as though on the face of it that JASP is kind of like a hybrid combination, if I was going to describe it to some people, as effectively as a hybrid of Excel maybe and the Jupyter notebook in Python. So I kind of like to leave it like that as a broad description, because some people might disagree with that. But basically what it does is it gives you out of the box statistical functionality that you never had to kind of like build or so like understand the well, it always helps you having an understanding, but like you didn't have to construct the inner components of kind of like how your standard deviation or any other stat was created. So in some of them here, they might be a bit too small to see, but you see this like ANOVA and regression and so forth, and you can sort of like click regression and get a regression line and so forth, and you can do that, you know, in a whole host of other languages and so forth. You can do that in Excel. So this is one nice way of doing it, and it offers you this nice feature of doing it, but also it lets you copy and paste the charts and the data out of the application and paste them straight into your document, which is very, very convenient for users. So it looks like a really, really user-friendly interface. And here it says dynamic updates of all results, spreadsheet layout, and an intuitive drag and drop interface. So it's kind of like got all of them, I guess, all of the features. And I guess if I wasn't a computing person and I wanted the data science component, that this is actually a very nice out of the box package that gives this to you. So I scrolled down, and this was actually I think I don't know if I hover over it, but you can see this is the 4 or 5 minute video that I watched, and then I watched another video on that just to kind of like do a global assessment of it. And you know, here's a whole bunch of people that have contributed, or the scientific advisory board, but it's much bigger than that, and I think there's a GitHub and so forth on it as well. What was quite interesting was I went to another video, and it says that JASP was, what does JASP stand for? It's always interesting where these acronyms come from, and JASP stands for Sir Harold Jeffreys. So it stands for Jeffreys Amazing Statistics Program. That's what it stands for. J is for Jeffreys Amazing Statistics Program. And I thought I'd go and Google him up. I wonder if I've still got it there somewhere. No. I did actually Google him, and so I've obviously lost that. So Sir Harold Jeffreys in my search. Anyway, there we go. Sir Harold Jeffreys. And so it's kind of like, I think it's quite nice because it was either created by him or started by him, or it was named after him, but one way or the other. That's quite a nice sort of like backstory to it. But he was a British geophysicist, 1891 to 1989. So maybe he was kind of like the creator or the beginning of it. But basically, he made significant contributions to maths and stats, and this is a stats package. So Harold Jeffreys was a British geophysicist who made significant contributions to mathematics and statistics. His book on the theory of probability, which was first published in 1939, so before the computer age, played an important role in the revival of the objective Bayesian view of probability. And we can sort of like go in and have a look at those things, but I guess we understand what JASP is about, and it kind of like accumulates these statistical methods, and then you can spit things out of it. So anyway, the JASP is a open source, I believe a freer version of SPSS, at least that's how it sells itself. I have not used either of them. SPSS is, I believe it's supposed to be like a better version, but it's a paid for version. I'm not going to say that it'd be wrong to say better. It's a paid for version of what JASP is. So I understand again that it's taught at some schools and universities, but then when you come out, unless you're in industry and your company's paying for you, you probably won't be using SPSS on your own. And it's probably a bit like Microsoft Excel versus maybe Google Sheets or something, where one is a paid for version, you have to subscribe for it. So if you're on a student's license, it's fine, and if you're working in a company, then it's kind of like covered by that. But if you're an individual on your own, then it's not. And here's a rival here. This is SPSS, which is an analysis tool for data. So you might have come across this before. It's a user interface that looks like Microsoft Excel, and JASP kind of like has that same kind of interface that also looks like that. Let me just put my phone off because I don't want to have loads of noise. And so yeah, it looks like Microsoft Excel, so they both look like that, and it's set up as a spreadsheet, and then it kind of like mentions MATLAB, Minitab, Power BI, Stata, MySQL, Tableau. So they will all mention these types of things because they're all operating in the same way, and basically, whatever version of things that you're using, ultimately you have this table. We'll call this table a data frame in some way, and so if you're using like a MySQL database, it's one table of the database. And if you're looking at a Microsoft Excel spreadsheet, then it's like one tab or an area of the tab on a sheet, which is effectively your table. And the same thing for Power BI, Tableau, MATLAB, and so forth. So I come at it from the approach of Python, which is Python will have the data frame, ultimately the pandas data frame, which is its version. The community on Python is, I think it's about 8 million or something, which is about 4 or 5 times larger than R, and JASP leverages off of the R language to a reasonable degree. That's kind of like where it's come from, and that's more focused on statistics. So Python's more general purpose, and over the previous 4 or 5 years, Python has grown in size, whilst R has shrunk in size, but it's been for other reasons. But basically, I guess the larger community, the fact that Python moves is this is cross-platform, but the fact that Python actually moves, it's a general purpose programming language, so it gives users more flexibility, has enabled it to have a bigger community, and then also the advent of not just data science but AI as a key component of data science has kind of like moved Python further up the popularity charts at the detriment of some like languages like R, and then some things like MATLAB and so forth, which will have suffered as a result of it, because users can't like pick their core expertise and they move between one or the other. So the community is of finite size. If people are migrating towards Python, that will increase it as its percentage of the market, and something else somewhere will give as its percentage of the market. And the main languages are JavaScript, Python, C++, C, those types of languages, and Java as well. And then that doesn't mean it will stay that way, but that's how it is at this current point in time. So anyway, aside from that was kind of like a little review into JASP. It's kind of like looking at that functionality, and I kind of like I think, well, from Sir Harold Jeffrey, I don't know how I managed to browse through. Well, I do know, because I think this was, let me go back on this, well, Harold Jeffreys, and I believe I clicked on something near Durham, north of England, so there we go. And I'm not even sure, I probably, yeah, I did, I clicked on curves there. I was like, oh, what is this? I clicked on curves, and I felt, you know, I'll try and go into this, but I'm going to take the Python approach again. Like, I imagine that some of this stuff may or may not make its way into may not make its way into JASP. But I thought I'd do this, and I thought I might do this from a Jupyter notebook perspective. And as you know, generally speaking, I do everything in this, like in the videos that I do, everything's out of the box and kind of like brand new. So I've clicked on a couple of these links here, and that's kind of like it. I was like, okay, well, I don't even know what this is, the Lamicon of Pascal, but this curve. And I was like, well, you know what? Let's just see if we can get some of these, because they're quite interesting working in Python. I thought maybe I'll even do an entire video on that. The Devil's Curve, that looks like an interesting one. It's got a Cartesian equation, and it's got a polar equation, so I'm going to have to remind myself of A-level mathematics. That's going back some years, but you know, that will possibly be interesting. Again, here I'll just zoom in so we can see the two equations. They're probably a little bit clearer now. There we go. The Cartesian equation is this, which is y quadratic in cubic, no, more than cubic, to the power of 4 in y and to the power of 4 in x. And it's got a polar equation as well that's got tan squared thetas, and I haven't touched those kind of things. So trigonometry, there's going to be two ways. View the interactive version of this curve. Okay, let's have a little browse of that. There we go. Okay, no, doesn't work because the mouse wheel event could not be loaded. Okay, maybe that's because I tried to do, I don't know what you can do on this. Evolute, there we go. Involute. So there's a couple of different things that can be done. You know, I've done some of these. I wonder how this is actually done and what was given. Let's increase some values. There we go. It does certain things. And I don't even know what these things do. Does that just shift it across? I think that's just moving the chart. Yeah, that just looks like it's moving the chart across, so not very much there. Shrinking it. Okay, fine. So some of these are just, I guess then possibly not doing too much. But anyway, maybe we'll try and build some of this curvature, some of these curves. So let's just jump into it and do some code. But the first thing I've got to do is I've got to remind myself in Python how to get code working. And I was kind of like, I had a little play around, and I thought, you know what, I'm going to just do this all live. So this is how it's done. There's nothing pre-done here. But the first thing I'm going to actually do is remind myself how to, and I started doing MP, and then I stopped over there, MP for NumPy, because this is about all I sort of like remember, and then I'm going to build everything from scratch. I'm going to use, and I again began doing this, and I thought, you know what, I'm going to kind of like do it from scratch so that everyone can see how it's done, and I can sort of like, I don't know, I'll just build it on this little video and see where we get to. But I think I was going to just start with a straight line and get a chart. That's kind of like where I was going for, and here it is. NumPy. I'm going to use NumPy. Why do I want to use NumPy? Well, potentially because I see some more complicated things here, and maybe NumPy will handle some of this stuff, not all of it, but not so much for, let me click on that again, not so much for this, because that's just a straight line, so that's going to be my x-axis. But actually, when I do the y-axis, there'll be funky things going on, and it's probably going to be better in a NumPy array than creating a Python list. Although Python lists are flexible, and I could do, I probably could do nearly all of it with Python lists. but I'm going to use NumPy for completeness. So the first thing I'm going to do is not this here, as I'm actually going to, I'll take this code out because I might as well, but I'm going to go into another folder here. I should move this, I will zoom in on this as well. Let me just create the other folder in, and I don't know why I'm going to do it in here, but I'm going to do it in the physics section. I decided I should make, oh, I've got a matplotlib charts version. Okay, let me put it in here then. In that case, new file. So I'm already changing tact and I haven't even begun. What's in this assets folder? Okay, animations. This is where I actually try to do animations, so animated plots. So I'm going to make this a new folder here, or should I just do, I'm just going to make a new file actually. I can make folders afterwards if I want to. So new file, and I'm going to make a Jupyter notebook. I normally do Python files. Now I'm going to make a Jupyter notebook, and we'll see why. But basically it's because Jupyter notebooks give you, you can muck around with your output a little bit more. They're a bit more user friendly, and this is more, I might migrate to doing some JASP stuff, and JASP looks close to a Jupyter, looks closer to a Jupyter notebook than it does to just a Python file on its own. So let's just make this, I'm going to call it curves, many curves. I might only do one curve, and it's not a Python file, it's a IPYNB, a Jupyter notebook. So I've created this notebook, it's blank at the moment. I'm going to now remove this bit. I'll hit clear down the bottom over here, and I will, in fact, I will have that in there. I will make this large, and also I will zoom in, so Control plus. There we go, nice and fat. We can see our line kind of like ending here, so there's plenty of space down below. So the first thing that I was going to do, which I did copy the beginnings of it, and this is normally the trio, so copy, there we go. In fact, I can do cut because I'm not going to do it here. X, there we go. I'll take the whole lot out there. I can hit save on this anyway. We're not going to be using that, and over here. Basically, I'm going to paste that in here, and I just want to make a straight line. You know, I could just go to NumPy. Probably should have the NumPy docs open, but to make a straight line, basically, you know, NumPy generate an array with 10 points. That was enough for me to prompt the Claude AI to give me a straight line. So I'll do the np.line space, and it tells me what it is. It just reminds me. I could go to the docs, but it reminds me of this, which is a start, a stop, and the number of points that you want. So I think that might be sufficient. I've got that. Okay, fine. So basically that. And I probably want to start at 0, and I wonder, I mean, I guess I'll just do that and then print X. Basically, one thing about the Jupyter notebook is you get to explore everything straight away. It's asking me for what Python I want to use. I'm using Python 3.11. Apparently in Python 3.13 or 3.14, I believe, so not the next version, but the versions after, there will be no GIL Python. Those of you who know what the global interpreter lock is, it will be removed, and apparently that's going to be very good for parallel computing, so, or multi-processing, sorry, and yeah, that's in a couple of versions time that's coming, so I think some people might be looking forwards towards it. And the reason that's being brought in is to because a lot of the data science and the AI type packages rather than data science, they use multi-processing. So Python and the global interpreter lock created some problems for that. So Python is is keeping up with the times. Basically, it's modernizing itself to keep up with the times. It's going to remove the global interpreter lock possibly, but that's a side note. So what have we created here? We've got x equals line space 1010. Okay, does it tell us what line space is? It's got a start, stop, number of points. I guess the nice thing about this is I just put in 10, so it's given me, it starts at 0 in there, but I've got these fractional bits. So I just wonder if I went to 9, because that's 10 points computationally. Remember that arrays start from 0, so an array, the first item is 0, index 0, then 1, then 2, then 2, dot, 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 and the last one would be, it's either 9 inclusive or 9 exclusive. I thought that maybe if I went 0 to 10, that it would actually do 0 and then up to 9, but it didn't here. So if I just run that now, that's a bit cleaner. We haven't got the decimals, so 0 to 9, and it's 10 units, so kind of like nice. I wonder if I remove this out of here, if it automatically does it. Yes, it does, and it looks like maybe it's done it every 0.1 or something. So there's obviously a default in the line space here. Let's have a look. Parameters, a start, a stop, and you see here, I presume that this is num, or is there a step value somewhere? Okay, num equals 5. And I believe that third value, I'm just imagining it must default to, well, it obviously has defaulted to something, but I'm wondering what it's defaulted to. Evenly spaced samples calculated over the interval, but if you haven't specified it, it's clearly doing something there. The end value of the sequence endpoint, number of samples to generate, default is 50. There we go. So I could actually test that out, because I could do len of x. It should have get thrown us out about 50 points. There we go, that's a 50, so it is doing that. So we could kind of like be lazy. That will give us, oh, we've got an option now. So num equals 5. There we go, or 50. I'll do 10. Keyword argument. Starts, I could put in here a start and a stop, I guess. But that's fine. We understand what line space is. It works a bit like the range object, but it's a bit more memory efficient. Anyway, we just want to get a straight line. So, and I actually could have written kind of like straight line in matplotlib. But I guess we will do, that's our x points. Yeah, so our y points actually, y equals x. I think that would be suitable, because if I just do y now, it would just be that, and we get an array as well, which is a numpy array, and I'm keen for this to be type of this, and yeah, it's an numpy.nd array, so fantastic. And then we just want to plot a chart. So plot is kind of like the simplest chart, I believe. And then x comma y is sort of like the starting point for everything. And then I don't even know if I have to do a plot.show here. Oh yeah, well, if you don't do a plot.show, then you get this jargon that comes up. So I think I might do a plot.show over here, just like that. And does it run it a little bit cleaner? But that's our straight line. There we go. We've got our first curve. Our curve isn't very good, because our curve is just a straight line. And I think it's something like, I want to do an ax.plot, and because it's a bit, but let's just do a plot, because we're actually doing things a lot simpler. Maybe we can get away with it. Plot.title is a straight line, so I've done nothing more than a straight line still. And plot.x, x label, there we go. So I have to have a little guess at some of these things, but the x label is x values, and plot.y label is the y values. There we go, and let's just run that, and there we go. So we get our chart that's kind of like working. So at least that's the crux of the beginning of it. So we've got that working. So The next thing to do is something better than a straight. We have to achieve more than a straight line now. This is where the challenge comes in because I've not got a clue, so I'm going to be doing this from the beginning. So let's make a new chunk of code, and we can add our code like this. We can add our code from here like this. Is there a shortcut as well? I don't know. Let's have a I wonder if can we add a block of code some other way? Now anyway, I always just click on here to add our little block of code. So we could have code, or we could add some markdown. We're not going to put any markdown because at this point it's relatively simple. So this is just a straight line. I might actually, we don't always need to import the NumPy, pandas, and matplotlib and so forth, but in fact I didn't even use pandas here, it's grayed out. So I'm just wondering, do we do the minimalistic and show each block kind of like piece by piece? Let's just see where we get to on this. I'm going to jump back to the curves, and I think that I might go over to something. We've done a straight line, something possibly relatively easy, but I might be able to chat GPT, well not chat GPT, but I might be able to Claude AI one of these easier ones and kind of like go from that and sort of like extend from there, because that's the best way of doing it in a way if you're going from the beginning. So nothing that I see here actually, funnily enough, that's easy. The ellipsoid, unfortunately for me, looks like the easiest. So hyperbola, frequency curve, okay, maybe. What was a hyperbola? Possibly, if we generate a bunch of x's, we can square our x's. We can get some y's. I wonder. I might actually attempt to do a parametric curve live and fail. It's supposed it'll probably be very easy actually doing it. So I'll start with Cartesian because that's our Cartesian equation that we've got. So let's just try a hyperbola. There we go. Actually, before we even get to a hyperbola, let's just do a quadratic. So straight line, I'm really going to take baby steps here, but let's just do, we'll change that to and so something like, I imagine, like y equals, we could just start with x squared. Okay, the computational version, by the way, of squared, if we're going to do the notation in Python, is that. So I'm going to stick to that, but we're going to do y equals, we could do a y equals x. We'll just start with a y equals x squared, and we'll extend it to this maybe, a x squared for our practice. So a times x squared plus b times by x bx plus c. So the standard quadratic equation there. So I will put a double spaces between these pieces just so that maybe, I don't know if that's a little bit clearer, but we're going to go for that. So the first thing we're going to just do is y equals, in fact we just do x squared. I'm just going to start with an x squared, and we should just be able to plot that. This is quite easy, easier than I expected. There we go. So we got y equals x squared, that's fine. We're now, if we want to do ax squared plus bx plus c, we're going to need to have some variables go in here. And this is where kind of like, I guess, I prefer Python over the notebook, which is that you can start putting things into functions and kind of like building and reusing your functions, whereas in the notebook you tend to be copying and pasting code. They're kind of like two different alternative options, but we need to have an A and a B and a C. We can use a tuple here. The tuple, we can do this. Can't remember what it's actually called when you do ABC. What's the wording for it? Put it in the comments, or I might put it in the comment myself. But we can set A to be, I don't know, like 1. Let's set B to be 2 and C to be 3. There we go. So it's kind of like x squared plus 2x plus 3. That's what we're going to have here. So we're going to have y equals a times x squared. In fact, if I've written this all out properly, it's going to be all of this over here. Right, so I think we can just run this as is. Do I need to even clean it up? Okay, all about conventions and stuff. You know, I've just got one space between. Some people might say, here I've got two spaces in between, and that's actually for clarity. I could even put like 4 spaces in between. The reason why, like, you could ask why I've done this, but it's just to isolate the formula so that we can see the component parts of it. I could stick all of this into brackets, so this is the first component, this is the second component, and this is the third component. There's different ways of kind of like showing what it is. I'm just making it very, very explicit. That's kind of like what we're doing. So now we've got our, this is no longer a straight line. This is a quadratic. There we go, quadratic equation. And I haven't done any colouring or anything else, but maybe we'll start introducing some of those to turn the line to red. I don't know, for example, plot dot colour. I think C might just be colour, but actually I'll be explicit in that equals like red. I don't even know if that's going to work. Yeah, it does. There we go. Fantastic. Make it dark red. I'm really pushing the boat out here now. Yep, good. Okay, so some of the stuff that I remembered works. So again, if you don't like when you don't know this or so and so on, that may be that you can call it out. Now I can't remember if the points, like how to put like the points. I wanted to like specify it, but like let's have a look. Like marks. No, okay. I'm going to be really fast on this because I want to. If I draw a curve with matplotlib, how do I get the points to be circles? I'm kind of like just prompting. I could, like, you know, videos, the older version of videos would do something else. There we go. I actually wanted to explicitly have the marker site. Okay, fine, but it doesn't have it, so I'm just going to do that then. Copy that. There's nothing to do there, which is actually might ask for it. But if I put that in there, that will put little circles on there. Oh, and I actually want the line as well. Oh, I know what to do there. Okay, fine. I feel like remember. It's prompted me to remember, but I think it's something like O minus or minus O, one of the two ways. There we go. So we can now see our quadratic and how it's built up. And if we remove this number equals 10 here, that we now just get our default version and we get 50 points. So it looks like that. We'll keep it at 10 for now. Num 10, there we go. So 10 equally spaced points on our chart. So we've got that. So we've got a quadratic equation as well, but that's not very good still at the moment because we want, say, our quadratic to go from -9 to 9, because then we'll see the shape of the quadratic, hopefully. And there we go. That looks a little bit better. And it looks like I might even have to go further back. Maybe now it's time to, I don't know, num equals 20 because we'll have more points there. Let's just run that. A few more points, we see the curve a little bit better, and that's probably not inclusive, so there we go, 10, there we go. I don't know if it goes back enough. I wouldn't think it's the same height, but there we go. We get this smile, this quadratic smile of some kind, and we get the minimum point. We can do other analysis on it, but we now want to move on to the curve. So I've been too scared to move on to the curve still, but let's create this new one. Now we're going to go into new territory, Control S, because some of that was already there. Let's have the quadratic line, and where was our stuff? We are now going to do a hyperbola. So the hyperbola is going to look like, I think this is quite a nice demonstration of the Jupyter notebook, in the sense that you can do things literally out of the box straight away and pass them in without, like, I've never done a hyperbola in in you know, the Jupyter notebook, like in Visual Studio Code and Jupyter notebooks. I've never done it before. This is kind of like a first time, but it's in literally seeing someone navigate through for the first time. Let's just see how it works out. But the first thing to do is, I guess, take this. And by the way, like one thing that I could do, Control Z, I'm not even going to call it cheating, but it's kind of like draw a hyperbola. I was hoping to be able to do that, but I couldn't. So basically, it's something like x squared. So x squared, and what was it? Divided by a. I wonder if that was over a squared. Yeah, it was over a squared. But this parameter here, this a, is actually, we could look at it as being a constant, like mathematically. But anyway, the next component of it is plus, and then y squared over b squared. So y squared over b squared. And just for the sake of computational clarity, 2, 3, 4. I'm going to stick loads of spaces in there, right? And I presume that hyperbola, everything is okay. It's equal to 1. I was going to say it's equal to 0. Equals 1. So I'm going to need an a and a b, and not a c, in the hyperbola version. We don't need this thing over here anymore. And I probably have to rearrange the equation, at least if I want to draw it. I want to draw this equation in the format of, I wonder if that's working, but basically, I don't know, my pen doesn't work again. So, okay, I might try to get it working. Let's go back. Right, looks like the pen's working now. So, I'm going to try to get it to look, because this is our x values here, and this is our y values here. So I need to rearrange this equation such that y is equal to, y is on the left hand side of our expression. So we want y to be here on the left hand side. Left hand side is going to be y, and it's going to be equal to, and then the right hand side. So I'm going to have to RHS for right hand side. So I'm going to have to rearrange this equation. I've got to do some mathematics here to achieve that, to get it in the right format, so that we can, given an x, I wonder actually, yeah, because given an x, we know how to square our x's. That won't be a problem. So we'll be able to create all of our x's, but our y's, okay. I will iterate towards the right answer, so you can watch an iteration towards the right answer. But if I was to rearrange this, the first thing that I would do is take this whole equation, stick that on there, and I've got to move all of this beast over here. X, take it all out, and move it over to here. It becomes negative on the other side because I've got to take all of that away. And then that means we don't need this plus over here. And then I've got to multiply the left hand side and the right hand side by b squared. So that means that this, if I x basically, or I'll show all of the components of it, but basically imagine that was in brackets and I multiplied, so I'm going to have to multiply everything here by b squared. I do this in my head, but I'm just showing it explicitly, kind of like what's done. So now we've got y squared is this whole expression here, but then we can expand the brackets. This is the first term in the bracket, and this is the second term in the brackets. Well, the first term in the brackets is quite easy because it's just, I'll leave this line in actually, I'll keep that one there, and I'll move on to the next line so we can see some of the working out. Copy that, paste it there. Now if I cut that out, it's going to multiply here to be b squared, and it will also be a multiplier here, so paste it over there and then times by this, right? Which means that we've now got the two terms that we want with the b squareds, like that. And we can tidy this up a little bit by taking that out and just putting it over here like that, just because it's a little bit nicer. And that means that I don't know which one we're going to use actually, because this one might be sufficient. In fact, I'm kind of like thinking that I was good enough here, because I've added no more value by doing that. So I can kind of like leave it here. Right, this is good enough. This, there is good enough. In fact, I'm going to take that this is good enough, because the only thing we then need to do, given all of this, is compute the value of y, which will be over here. It's going to be y is going to be the square root of our whole expression here. So of everything in here. I kind of like computationally, like I sort of like put these extra spaces in just for visual clarity. I'll put one more in so we can, like, some people frown upon it, but I kind of like I started doing that a lot in Excel when you've got these much bigger formulas and you're like combining them in, and then it becomes, and in fact what I do is break them down onto lines, and it's just clearer to see. So y is the square root of it, and it's actually, I guess it's going to be plus or minus the square root of it. So I've got to be sort of like careful of that. But let's just leave that as it is, because that's sufficient. Now, when I was saying that this piece here, a squared, is just a constant, and b squared is just a constant. The reason why is, like, we've got a and we can square it, but then it's never changing thereafter. So and b is the same thing, we can square it. I think that's the case, that we're never changing them. I've just got to remind myself by having a look at that and thinking about it for a second. But I believe, well, actually we'll get a little hint here actually, presumably. I guess you can choose different values of a and b. You can choose different values of a and b, but we can do that anyway. So I think that's fine. And actually, oh, the mouse wheel thing again, that popped up. I think it might be cleaner in a way actually doing this parametrically, because this is putting it, I imagine that this is putting it into polar coordinates is what it might do. And yes, this is JavaScript there. I was just kind of like looking for that down the bottom somewhere to see what it was, but it's going to be JavaScript or Java. It's always going to be one of those two. If it's in the browser, it's JavaScript. But anyway, yeah, so we've got that. We're doing it in Python. I guess we could do it in like Plotly or something, and also put it on the web. Python's got its web version, but we're just doing it in the Jupyter notebook now. So let's just pull a Jupyter notebook up and let's just run through it then. So we've got x, which is still a whole set of numbers now, going from like -10 to +9, you know, which created like this x value, our x values over here. And now we need to compute our y, but we know how to compute our y. In fact, I believe I could probably take all of this and paste it straight into here again if I've written it out nicely. And I need to do one more import now, so I'm going to do a bunch of imports. Whenever I have to do a new import, I'm going to do a whole bunch of imports, which is, I'll take this, but it's basically the math module. Or actually, I don't have to do too many more imports, because I can leverage off of NumPy, because I'm sure NumPy will have a square root. So, but here is one thing, which is if I do an import math, this is quite useful to see, is I can do a math, because there's something about aliasing, right? Because I could have done at least math.square root there, but I think probably we could have had an np.square root. And we see that we've got the same thing here, and I have seen this done, so kind of like don't do it, I'll mention it, but import or from math import everything, right? And then from NumPy import everything. Now what's going to happen here is that now you've got math which is available, but where's it come from? Has it come from the math module, or has it come from the NumPy module? Because you've imported everything. So to avoid naming collisions, this is like the perfect example. If I want to have the square root function coming from math, I can, and if I want to have the square root function coming from NumPy, I can, but they're distinct from each other now. I don't need, because we're still catered for with NumPy and already imported the module, we'll stick with the np.square root. It probably fits a little bit better. So I couldn't just do square root. I had to do it from because it's not a natural function in Python, it's an imported function from the module. The square root thing is going to be in a lot of modules, but we're going to take the np.square root of all of that expression because that was a square root, and everything else looks like it might be fine. I've got no idea what's going to come up, but this is going to be our hyperbola. Oops, copy that and paste it over here so it's no longer quadratic, it's a hyperbola, and just hyperbola, I guess that's all it is, and plot.show it. We're going to run it, control return. I don't know what happens. Okay, that didn't look too promising because, hold on, what's happened here? Runtime warning, invalid value encountered in the square root, np.square root. Okay, because I guess that a squared here, let's like debug it in our minds, but a squared is just going to be 1, x squared is going to be 1 here, and 1 minus 1 is going to be 0. Now that should be fine. Invalid. Maybe I'll print out y. Print y. I know. Let's run that. We get nans, a whole bunch of nans, right? np.square roots of. Okay, it's probably my implementation at this point in time. Can I? Does it not? Why does it create an error message there? 1 minus x squared. Let me just try one thing quickly on this, which is y, and then I could always revert to the GPT thing, but I'm going to do np.square root just of x over here, for example, and move this one out, and so like move this one out and see if any error message comes out. So that looks okay. That's looking at relatively fine. I can actually print what y is again. Oh, hold on. Let's comment this out and run it. We still get an invalid counter, invalid value encountered in square root np.square root of x. So, okay, I'm just going to revert to this. Given a NumPy array of x values, get a y array of square root of x. Right, just to make sure, because what I think is I might not have used my NumPy stuff correctly, but let's have a look. No, that's fine. Let's have a look. It's because I've got negative values in there. Right? I should have spotted that straight away. The curve that I'm going to have is only going to be valid for, because I didn't read the error message correctly. I was too quick. But now it's just occurred to me when I've seen this construction that if you've got negative over here, that is going to create a problem, but we can test for that empirically anyway, which is I'll go from 0 to 9, and that won't throw this error message anymore, and there's something that gets created without any error messages. And if I was to print this as well, now we get all happy values. And we can't take the square root of a negative number because it would create a, well, you can take the square root of a negative number, you just give you a complex number. But now this is fine, so it would print out our square rootings. Although I've got nans here again, 1 minus x squared, I wonder why. Am I creating still negative? Because I'm going to be taking the square root of a negative again. I wonder if I'm always going to be taking the square root of a negative. So that would be a problem, because when x equals 0, when x equals 0 over here, all of this is going to evaluate to, well, this will evaluate. Oh no, then I've got to be really careful with this. Have I done the maths right on that? 1 minus, let's have a look. Was anyone, when I rewatch this video, is that, no, that's fine. I multiply everything. I move the y over. So basically, y became 1 minus all of that. And then multiplied by that. And then the square root of the whole lot of that. Now, so b is not relevant, but here, if this number evaluates to a number greater than 1, so I've got to be careful of that. So let's kind of like shrink the values down. So in order for it to be valid, I just wonder if I stick in a is like 100. So this number now is, this fraction here is always going to be less than 1. And that would be sufficient for this chart to plot, run it, and that's now sufficient. So we've got some sort of hyperbola, but it doesn't look like a great version of the hyperbola. Let's just do that. That's fine because our y values are all positive. But what's going to happen basically is that we can only print certain parts of it. So I haven't replicated yet. I can control save just to make sure that's all in there. And we don't need to print out our y values every time. But it's only going to be valid for certain regimes. So I might do this, which is because I just want to actually compare my code to see how this works for matplotlib. And I'm going to go to the Claude AI and write the code to plot a. I wonder if I even get the spelling of the word right there. A hyperbola. Okay, a hyperbola. Oops, there we go. Using matplotlib and numpy. There we go. Let's have a little prompt and see what we get. So we import numpy, import matplotlib. We've got the line space. There we go. Okay, we can leave that. It's got the negative numbers in here. Calculate the values for the hyperbola here. Yeah, this is his b over a because I guess you could have taken. I wonder. Why is that not taking the square root? That's interesting. It's interesting that it's this and not the square root of that. Could I simplify the equation is the question, because can I simplify this? Because I've taken the square root of that. I'm going to need to get my mathematics stuff out of here, basically, which is because basically what we actually have, this looks like basically the square root, the right hand side of the expression is basically all of this, right? I am going to simplify this now, which is the square root of, I'm just going to say that a squared is that and b squared is that, right? So it's basically that. So it's 1 minus x squared a over b. But if I did multiply through by b, it's basically going to be b minus b over a. So it's like, it will look like that. That's what it looks like. Which means that simplifies down to this. I wonder if that was cleaner, because that's what, if I copy this out of here, copy, is it a case that do you multiply through both sides by b squared? I'm just wondering, because I was going to compare like that. Why does the square root disappear out of that? That's the question. Because y squared was equal to that. I'm going to take this formula anyway, over here, and just have a little inspection of it, because basically we can set that y equals, and then it's going to be this, basically. So we can comment this one out, and we can even print our y's if we wanted to, and run the exact same piece of code. But I'm uncomfortable with this mathematics, unless my math is wrong. If I was taking that equation, that doesn't look like the AI has done the right thing, but AI version, but usually actually it's right. But let's have a look. So that's kind of like Claude AI. There we go. Is it Claude? Claude AI. And let's even actually take, well, it's got a 5 and a 2 here, so let's take those. 5 and 2 instead of 10 and 2. And control return to run it. And it gives us this, which doesn't look any better, to be fair. So what I will do is take this. I sometimes do this. I'm going to try another language model here, which is Bard, and I can sort of like zoom in on that. So let me just go to the bottom of it, or new chat. In fact, I'll do that and paste the prompt in here, and hit return, and zoom in a bit while it's doing its thinking. Right, okay, this looks a little bit better. So I'm now going to abandon my technique of just building on my own, and I'm going to go with this. And I guess it's got a description here at least of what it is. The code will create a hyperbola with the asymptotes plus or minus 1 over a. Okay, I'm just going to look at this formula. This calculate a hyperbola equation. It's got the a squared minus b squared. Okay, it's got it like that. That it looks closer, or it looks okay. Z equals this. Okay, fine. So it's created an x squared. It's created a y squared. Xy equals np.meshgrid. I'm going to have to look up what that is. I'm imagining. Let's have a look at how it actually comes about. So we've copied that piece of code, and I'm going to go back to here. And I wonder if I should retain this. I might do, just for, I'll keep it there, hyperbola, and I'm going to put This version is incomplete. There we go, because I might remove it if the new version looks better, and then we just have to look up the extra piece. But we still imported NumPy as NP, we imported matplotlib as .pyplot as PLT, we're defining our parameters. This version here create a mesh grid of X and Y values. I've got to ask what a mesh grid is. I could hover over it maybe, and it might say return coordinate matrices from coordinate vectors. Make ND coordinate arrays for vectorized evaluations of ND scalar functions over. Okay, we can actually see what this actually is, because I wonder, can we I could plot, I actually want to show the values of Z basically, but it's going to do a contour plot, so I guess it's looking like the right thing. Let me run it first and then we'll print the value of Z afterwards. There we go, works. Okay, fantastic. We can nick a tiny piece of code, but not too much, which is basically this over here. Didn't need this comma because I didn't put it over there. And stick that straight into, I guess, over here. Colors equal, got colors equal black. Okay, I'm going to X this one out, and because it's got colors and color, so that's an interesting one. I don't even know what that's going to do. Let's have a look. I don't want to destroy it. Okay. Let me just remove the color. I'm just going to remove this one. There we go. Right. It hasn't done that piece. Funny enough, I'm going to take this out as well. Color equals dark, put it up and wonder. Okay. Doesn't throw much of a descriptive error message here. Following keyword argument. Oh, colors. There we go. Okay, so colors is okay, fine. So when we were doing, I guess it's because of this contour, and the contour is going to work in a different way, so we have to use colors instead of color. Okay, fine. Let's now print out, because that looks quite nice, although we were unable to get the points, so I could actually put here plot. This is one thing to note, which I've noticed a few times now, that Bard AI gives better results than Claude AI. So it's not the first time that that's actually happened, which is a little bit disappointing, but whatever, because I've been using Claude. I've been trying to use Claude a bit more, but I guess you've got to use the one that gives you the more correct answers. But plot circles. For the points. There we go. Just see, it's going to add in one extra little field there, because basically putting in the 0, thing didn't do it. Okay, that's probably a little, I might live without it, but basically what this does is plot the circles, which is it's going to create a whole range of values, and then plot a little circle on each one and fill the circle out. So that's, I don't know, is it too? If we do want to have circles, not that, that, which is this version here, if we do want to have little circles, that basically we're being told that I think we might have to do something like this. For I in range, radius I, what was plot circle, contour equals black, fill equals false. Let's have a look here. Well, that doesn't allow it because plot.circle, for whatever reason, is not valid because this circle plot.circle doesn't exist. So right, okay. So again, a large language model spitting out something that sort of like keeps you happy. It looked like it might have worked because it was going to do like I was hoping that might work and do that, but it didn't work. I could put the. I'm going to leave it out. We're not going to have dots on there for now, which would have been nice to have, but that's fine. But yeah, we do have our hyperbola over here, and what I wanted to do was actually print out the z values, because I think that we get this numpy array of z values. Here's got 1,000, so let's just reduce this to 20, and over here as well 20. That's going to be 1 in every point because 20 is the gap there. That's all it is. Let's just run that, and now it's much less. It's still what actually comes out in Z is there's going to be 20 arrays by the looks of it, 20 sub-arrays of arrays. There we go. So that's 1, 2, 3, 4, 5. Okay, fine. It's got dot 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 because it's. I'm going to make less 10 and 10. That's even less. There we go. Our crumbly, like non-curved one, because we haven't got enough data, our wrongly sampled one, should I say. But that's quite nice because we can see what's in here now, which is all of this over here. And so that's one of these, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so there's 10 lists here, and these 10 lists, so they're the 10 lists of Z. And Z is that parametric, but I wonder if that was sufficient, because let's just go back, clicking on here. No, Z wasn't that. Right, let's just go to our GPT thing. Where is it? Not a G. I keep calling them GPTs, but it's not. It's Bard. Let's pull up Bard. Let's make that kind of like big screen, and I guess it's going to actually. Did it describe it over there? Now here's a code to plot it. Oh, that was for the circles. Over here, hyperbola with asymptotes 1:1. The size of the hyperbola can be adjusted by changing the values of A and B. To run this code, you will need to do that. But I actually wanted to ask, what does this mesh grid do? Question mark. My lazy way of not having to go to the documentation. It should notice the question from the actual context in the LL model, because it would have recognized that mesh grid was here in this line of code. So I wonder if it said that at the top. No, okay, it didn't. Right. So the question, what does mesh grid do? The mesh grid function in Python creates a rectangular grid out of 2 given 1-dimensional arrays. Okay, that's quite nice. Right, it's going to take these 2 1D arrays, which is kind of like one of these, and so like one of these, and create, I guess it's going to do that, and it's going to create this rectangular version. It's going to do that. The output of the mesh grid function is a tuple of two 2-dimensional arrays, one for the x coordinates and the other one for the y coordinates. For example, if you have two one-dimensional arrays x and y, the mesh grid will create two two-dimensional arrays x and y such that xij equals xi and yij equals yj. Okay. The mesh grid function often used in conjunction with the plot.contour function to create a contour plot. For example, the following code. The one question that I have here is what is j here, because xij is j every value or not? So that's an interesting one. Calculate the function of values there, z equals k. So that's the final part, like the fundamental last question, because I'm trying to get my head around that myself, which is it creating a square array? Because if we just go into our code, what is this here? Let's make not minus 10 and 10, but minus 3 and 3, just for simplicity, for clarity, just to see what this is even closer. 3 and 1 again. We're going to get a really crude. Oh, we don't get very much. Okay, not enough there. I'm going to extend it a bit until it works. Okay, that's good enough. That this is okay, because it's still 10 wide, so I'm going to make this like 5 wide and 5 wide. There we go. Right, okay, that's better. So what we actually getting out of it, we're getting our x's over here, but which ones are the x's and y's? That's the thing. Is it a bunch of x's here? We can, I guess we can see, can we see the coordinates? 4 and something, comma, that's our x's and that's our y's. So plus 4 and minus 4 over here. That looks like our answers basically on the grid. That's all it basically is. Okay, fine. Because, and that's why we need the colors, because no, we can remove the colors argument actually. I wonder if I do levels equals 1, what actually happens there? I guess we get nothing out of it. Okay, so levels equals 0 over there. These are the numbers that come about, which is 0.751, 0.75 and 0, and that's symmetric. And on that side, I was wondering what they represent. 0.75, that's what it represents. Okay. 1, so that's kind of like the peak over here. Okay, fine. So one of these is creating the left-hand side and the other one's creating the right-hand side of it. So that's quite interesting. So I'm just going to copy this because it's our working version. So it's our hyperbola. And I think I'm going to do a follow-up video. One, explaining this a little bit better because I've got to get my head around it myself. But the other one is to then attempt to do, so we've done, we've done 2 man-made curves and we did 1 incorrect curve. But basically here we've done a straight line, here we've done a quadratic equation, and then finally not this one here because this one's incorrect, but this one here, if I remove the actual print of z's, is the hyperbola. And so like increase these values, I guess, 20 and go back to 20. this is the hyperbola over here, which is already, I'm going to say, reasonably complicated, because we've got this parametric type of thing going on, where we've got an x squared and a y squared, and kind of like computing that. I was going to try to do it my linear way, but it didn't work. So this mesh grid was a way to take this approach, which means that it's probably going to be the way to take the approach for many of the other curves that we're going to come about, because we will see, like our next curve. I'm just going to click on any of them, if I can go back enough, like this devil's curve, for example, because I clicked on that one. I was like, what's devil's curve? That we've got this same type of equation here, and it looks like I can't just do, well, here I couldn't take y out of it anyway, because there's y to the fourth and y squared, so I couldn't even move everything to the right hand side and take the square root. Not that that worked anyway, so I could like type in devil's curve into the language model, and to like have it go through. But I think for an understanding of what actually happens inside of it, it's better to construct them ourselves. So I'm probably going to terminate the video here, but there's more curves to be done. And actually, like, I guess one of the things to say is kind of like in the notes or whatever, if anyone's got a comment, certainly definitely like the video, follow, so forth, forward on to everyone else. But if you've got any comments, or kind of like have your own code already for something like the devil's curve, we can leave that in there as like the one kind of like example. Like, we've got the Cartesian coordinates here for the Cartesian equation for the devil's curve. So can we get this plotted in using matplotlib, basically Python's matplotlib in a Jupyter notebook? So can we get that work? That will be an extension to this. And I might do a follow-up video plotting some more of these curves in matplotlib. But what we do know is that it's doable, because we see that we've done the first one over here, this hyperbola, and we had quite a good replication. Our hyperbola in using matplotlib in VS Code worked quite nicely. One thing that I remember that I could have done, which is why I kept this open anyway, is the Jupyter variables, because I could have actually inspected what Z was over here and forgot about that. So that's our Z here. That's what it looks like. That's with the 20 by 20 across, basically. So we'll see it goes 20 down, I guess, and 20 across. It goes from 0 to 19, which is 20 across and 20 down. That's kind of like what it plotted out there. So forgot about that. Our Jupyter variables are kind of quite a handy little thing to have, and all of our variables get thrown into the Jupyter variables, so that's quite a useful feature to have on the side as well. So I terminate the video here, and look forward to seeing what comments we do get, and if anyone's interested in any of the other charts specifically or anything like that, definitely post it in the comments, and I'll go through and actually produce them. And again, I'm going to try to do everything that I do nearly unprepared, so it's kind of like live. If I fail, I fail, and you kind of like see me browsing through, because I think one of the useful things about it is how to debug and go through and find the errors and so forth. So that's how I'm going to keep these videos. So I bid you all farewell, and yeah, like the video.